with graphs, their terminology, and even representation behind us. Now we're going to focus on graph traversals, specifically a breadth first traversal and a depth first traversal. Now you might be thinking, hey, that's easy. We've done this with trees. In fact, there is a connection since a tree is effectively a graph, not always vice versa, but a tree is a graph. And we've done both depth first traversals as well as a breadth first traversal of a tree. A graph is a bit more nuanced, but it's not that bad. So hopefully this will be an easy video here. So the general idea is, what if you would like to list out all of the cities that, for example, United Airlines can reach from Hartford Airport, specifically from Hartford. So if we were to start here, we can see that we can reach all of those cities, just not DC. But from Hartford, we can clearly go to Chicago and New York. From Chicago, we can go to San Francisco or LA or New York or back to Hartford and so on. But clearly, you can see this graph here, all of these nodes are connected, and so they can clearly all be reached. Now, we can see that. How do we get a computer to see that? How do we get an algorithm to see that? That's when we come to this idea of a traversal over this graph. And so from each vertex U, what we really want to do is we want to list out all of the vertices that can be reached within the graph from that vertex U. And there's a process here. Again, there's a depth first process and a breadth first process. This is the general idea. Each node is going to have a flag that indicates whether or not we have visited that particular vertex. Now, the United Airlines example, a flag indicating whether or not we have visited that particular city. Now, from that vertex, we can then expand in some fashion. We can either expand downward, right, down this depth first path going through nodes, or we can expand outward in this breadth first manner. The way in which we expand is based on the traversal. Is it a depth first traversal? Is it a breadth first traversal? Still looking here at the general idea would be, we're going to start, for example, at Hartford, and we want to find, hey, who are the immediate neighbors that are connected to Hartford? Well, we can see it, Chicago and New York. So we have this list of neighbors that are immediately connected to Hartford. And then we can say, okay, well, who are their neighbors? Well, the neighbors of New York and Chicago now encompass San Francisco and LA. And then we can see there are no additional neighbors and we're effectively done. Again, this is just the general approach, but we can see that we are able to arrive at those 5 cities starting from Hartford. Of course, we cannot get to DC. So the general idea is all of the vertices are initially going to be unvisited. We have not traversed or visited any of these cities, of these vertices. Pick a starting vertex to be your initial point. And the example given, it was Hartford. So pick some starting vertex, and we're going to add this starting vertex to what we call a probing list. This probing list will be used both with the breadth first approach as well as with the depth first approach. And this probing list is really the vertices that are currently under consideration. Now, we may have visited those vertices, or we may not have. That's going to be algorithm dependent. But the probing list are the vertices that are under consideration, and that will make more sense when we come to the algorithm. But while this probing list is simply not empty, remove a value from the probing list, remove one of the vertices, mark that vertex as visited, and then do something with its neighbors. Either add all of them back to the probing list, add only one of those neighbors back to the probing list. Again, that's algorithm dependent, but that is the general idea. So the 2 algorithms are, again, the depth first traversal and a breadth first traversal. And so to make this complete, just a reminder, the depth first traversal is from a given node, we want to go as far down a path as possible, even reaching a dead end, before we back up and we look for another path. The breadth first traversal is we don't want to go as far down a path. Instead, we want to branch out as wide as possible, effectively checking the beginnings of all of the different paths next to me before going deeper down a particular path. So we're going to examine both of these traversals. We start with a depth first traversal. So with a depth first traversal, we're going to actually implement this probing list of vertices as a stack. So as a stack, which is that last in, first out data structure, we're going to implement that as a stack. Now you have a choice. You could implement that as a physical stack, or you could implement it as a recursive stack. But we're going to implement it as a stack in general, conceptually, and then you have a choice in code. Would you like that to be a physical stack as a data structure or a recursive stack in code? So here we have this graph. We see that A is connected to 3 nodes, B is connected to 3 nodes, C is also connected to 3 nodes, D is connected to 3 nodes, E is connected to just 2 nodes, A and D, and F is also connected to 2 nodes, B and D. And so here I just have a listing of the neighbors. So A's neighbors are B, C, and E, right? You can see that. What are the neighbors of C? Well, C can connect to A, to B, as well as to D. And so those are the neighbors of C. Not that big of a deal. So just listing out the neighbors, and we're saying we're going to start from vertex A. So here's the initial state of our depth first traversal. We have not visited any vertices, but since we're starting at vertex A will be already in our stack. And remember, our stack is really just this list of probing vertices, the vertices under consideration. I also show here the unvisited vertices. It's really going to be all of the vertices that are not in the visited vertices. It's the remainder of them. Now, since the visited vertices is currently empty, all vertices should be currently unvisited. This is just for a visual, a conceptual visual for this understanding as we go through the problem. So one more time, the probing vertices, which currently we're going to start by examining A, that probing vertices for this problem we're implementing here as a stack. So what's the process? Well, here we go. It says pick a vertex from the stack, pop the stack. It's A. Mark it as visited. So A gets marked as visited. And then we're going to really key, either you could pop A off of the stack, mark it as visited, and then we're going to check, does A have any neighbors that are unvisited? If so, we're going to put A back into the stack. So that seems kind of unnecessary. So you really could have just peeked, like look at the top value of that stack, which is A, mark it as visited, and then find A's first unvisited neighbor. Does A have any neighbors that are unvisited? If the answer is no, at that point we remove A from the stack, which you'll see shortly. In this case, though, the answer is not no. The answer is yes. We have an unvisited neighbor of A. The answer is B. Find A's first unvisited neighbor. So the neighbors of A are B, C, and E. All of them are unvisited. Which is the first unvisited? In this case, we're going to do it alphabetically. So you're going to write your own algorithm, but in this case, we're going to do it alphabetically. A has 3 neighbors. Let's choose the one that is, of course, unvisited. That is lexicographically the smallest, alphabetically the smallest. So A's first unvisited neighbor, which is B, we're going to push it into the stack. So the probing stack of vertices included only A. Now it includes A and B. Now note, we did not remove A from the stack. Why? Because A had an unvisited neighbor, which was B. So A stays in the stack. So now the probing vertices is A, and B is at the top of the stack. But we've only visited A. We have not marked B as visited yet. It's important. When we put a value into the stack, when we're doing a depth first traversal, we do not mark it as visited. We only mark it as visited when we are at the top part of this algorithm, picking a vertex at the top of the stack, mark it as visited, then check, does it have any unvisited neighbors? So let's come to the next slide. Follow the algorithm. Pick a vertex from the top of the stack. Well, here on the left is the initial state of this iteration of the stack. B is at the top. Mark B as visited. So now we have A and B are both visited. Here's the remaining vertices that are unvisited. And what does it say now? Does B have any unvisited neighbors? Well, look here. What are the neighbors of B? It's A, C, and F. Here's B, A, C, and F. Well, A, C, and F, A is already visited, but C and F are unvisited. So pick B's first unvisited neighbor and push it in the stack. So which is going to be C. It's highlighted here in red. we're going to push C into the stack. We did not remove B from the stack, again, because B had an unvisited neighbor. Next iteration, pick a vertex from the stack. That vertex is going to be C. It's the top of the stack. We're going to peek it. We're going to ask, well, first we're going to mark C as visited now. So C comes into this list of visited vertices. We're going to mark it as visited. Find C's first unvisited neighbor. So what are the neighbors of C? A, B, and D. Well, we have A and B. They're already visited, but D is unvisited. So we're going to find C's first unvisited neighbor, and we're going to push D into that stack. So here is the resulting stack after this iteration. And so now we have this probing list of A, B, C, D, which is our stack. Our visited vertices are A, B, C. Let's come to the next iteration. Pick a vertex from the stack. At the top, it's D. Mark it as visited. So now we have 4 visited neighbors, or 4 visited vertices in total. Find D's first unvisited neighbor. So does D have any unvisited neighbors? If we come to the previous iteration, we were at D. Well, D is connected to C, E, and F, as you can see here in the graph. You can also see over here. It's connected to D, C, and F. It's not written alphabetically. It's okay, though. And so, but D is already connected to C, and C is already visited. But E and F are unvisited, which is the first one. It's clearly E. So we're going to do what? We're going to push E into that stack. Next iteration, pick a vertex. That vertex is going to be E, right? We just pushed E into the stack on the previous iteration. So here's something new. So now what's the algorithm? We're going to pick the next vertex. That vertex is going to be E, which is at the top of the stack. And what's going to happen? When we pick vertex E, the algorithm says, mark it as visited. Well, it's already visited, right? Actually, no, it was not already visited. I'm looking back here. E, we had just added it to the stack, so it was not visited. So we're going to, on the next iteration, we pick the vertex at the top, we mark it as visited, but now here's what's new. After marking E as visited, we're going to say, does E have any unvisited neighbors? And we see, well, E has 2 neighbors, which are what? A and D, but A and D are both already visited. So what does the algorithm say? If there are no remaining unvisited neighbors of E, pop E off of the stack. Remove E. It's no longer under consideration because all paths from E have already been taken, have already been explored. There are no remaining unvisited neighbors of E. Pop E off of the stack. Done. So now the visited neighbors is A, B, C, D, E. But we have removed the E from the list of probing vertices. Now the list of probing vertices, which is that stack, is A, B, C, D. We come to the next iteration, pick the value at the top of the stack, mark it as visited. Now you might say, well, that's kind of unnecessary because D is already visited. No harm, no foul. It's just a Boolean flag. We're going to mark D as visited. After we mark D as visited again, we're going to say, are there any unvisited neighbors of D? Well, who are D's neighbors? It's C, E, F. Well, C is already visited, E is already visited, but F is not in the visited list. All right, so we don't need to pop D off. Instead, we're going to do what? We're going to find D's first unvisited neighbor, which is F. We're going to push it into the stack. Done. And now you can already see everyone is visited. There are no remaining unvisited neighbors. So what really remains of the algorithm is pop, 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 pop. But let's walk through that. So here, once again, we're going to pick the vertex at the top of the stack. It's F, mark it as visited. It's already visited, no harm, no foul. And then we're going to check, does F have any unvisited neighbors? No. What do? We pop F. Well, when we pop F, now the stack will only be A, B, C, D. The next iteration, before I click to it, let's talk about it. See if you can actually think about what's going to happen at that next iteration without even looking at it. Well, we're going to have to examine D, mark it as visited. It's already visited. No harm, no foul. We're going to ask, does D have any unvisited neighbors? It will not have any unvisited neighbors. So then we're going to pop off D, and the stack will have A, B, C. Here's that slide. We looked at D. We marked it as visited. We checked, does D have unvisited neighbors? It does not. So therefore, we pop D. The next iteration, we're going to pop C. We're going to pop B. We're going to pop A. And so here was a depth first traversal of our graph. What was the order in which we actually visited those vertices. We didn't actually write that down here, but that would be a good question to have actually paid attention to. Well, we're at A, then we add B, right? Then we're visiting B next, and then we're visiting C, then D, then E, then we're visiting F in that particular order. So that is a depth first traversal of our graph. That's it. That is your depth first traversal. Let's now go into the breadth first traversal of this same graph. So now we're going to implement this probing list as a queue, as a first in, first out data structure. And that should not be surprising. That's how we actually implemented the breadth first traversal of our tree. Going level by level, we implemented that with a queue. So we're going to use a queue for this probing list. We have the same graph, the same neighbors, the same starting vertex. So a little bit different here though, the algorithm. Of course, instead of looking at the top of a stack, we're going to look at the front of the queue. Instead of popping a stack, we're going to do a DQ. But the slight difference, the nuance here, is that when we look at that value at the front of the queue, we're actually going to enqueue all of the neighbors and mark all of them as visited in one go, which is how we're going to get this breadth first approach as opposed to depth first. So we actually start off the algorithm by putting A in the probing list, which is what we did on the depth first traversal. We started A in the probing list, but also notice A, we also go ahead and mark it as visited. Before we even start the loop of the algorithm, we say put A into the queue, into the probing list, mark it as visited. So in fact, I could have even removed A from this unvisited list of vertices. So that first vertex here, A, is unvisited, is actually visited, and it is not unvisited. The only unvisited vertices will be B, C, D, E, and F. So what does the algorithm say? Delete the first vertex from the queue. Make a DQ. Find A's unvisited neighbors, all of them. Mark them all visited in one go, and then put them into the queue. Well, if we're starting at A, what are A's unvisited neighbors? All of them, B, C, and E. Mark all three of them, B, C, and E, mark them as visited, and then put them into the queue. Now here was the initial state of the queue at this iteration. It said delete the first vertex from the queue. So we did a DQ, A is gone. And as soon as we DQ A, we find all of A's neighbors, and we mark them as visited, and we place them into the queue. We enqueue all three of them. So A's neighbors are B, C, E. We mark them as visited, and we enqueue all three of them in alphabetical order into the queue. That's it. What's the next iteration before I even show it? We're going to DQ B. We're going to find all of B's unvisited neighbors. We'll just look here at the graph. How many neighbors does B have? 3. A, C, and F. A and C are already visited. The only remaining unvisited neighbor of B is F. No problem. We're going to mark F as visited, and we're going to enqueue F. So let's take a look at this. The next iteration, we're going to have B, C, and E as the starting state of that iteration, and we're going to DQ B. We're then going to find all of B's unvisited neighbors, which is just F. And then what are we going to do? We're going to enqueue F. So if we have B, C, and E, and we DQ B, well, now we only have C and E here inside the probing list of vertices. So only C and E will actually be inside once we have DQ'd B, when we're then going to see which is B's remaining unvisited neighbors. It's only F. Mark F as visited, so F is now in the visited list, and then we're going to enqueue F. So here is the final state of the queue after this iteration. One more time, DQ B. The queue will have C and E left in it. We're going to take B's unvisited neighbors, which is just F. We're going to mark F as visited, throw F into the queue with an enqueue operation, done. Next iteration, let's look at it first, or think about it before we actually go to the slide. What are we going to do? DQ C, find all of C's unvisited neighbors, make them visited, and then throw them into the queue, which is really just D. So we're going to DQ C. So we started with CEF. We DQ the C. C is now gone. EF is what's remaining in the queue. And we're now going to find all of C's remaining unvisited neighbors, which was just the D, and we're going, so it was just the D on the previous iteration, it was just the D, and we're going to put the D into the queue after we mark it as visited. And now everybody's been visited. We're effectively done from that perspective that everyone's been visited. Now we need to actually clear out the queue, which is what it says: delete the first vertex from the queue. It's E. Check if there are any remaining unvisited neighbors of E. There are not, so we're done. And so we do the same thing again. DQ, we're going to end up DQing F at the next iteration. There are no remaining unvisited neighbors of F. You're done. Next iteration is D. DQ the D. There are no remaining unvisited neighbors of D. You are done. That is your breadth first traversal. Next slide. The queue is empty. We are done with the breadth first traversal. If you want to compare them, we have here, we can see a difference of the order in which we visited the vertices, of course, because one went as far deep down a path as possible and the other one went as wide as possible. So what I'd like to do is take a quick look at an example where we're just now doing this on here on a tablet, on a board, on a white paper, and try to do this along with me. Given this particular graph, we see it has what? 0, 5, 6, 7 vertices, right? From 0 to 6, that took way too long. We see it has 7 vertices. When we're going to do a DFS, let's start out and make this happen. And in fact, you likely recall the starting point for DFS is while nothing is initially visited, we do go ahead and put A, I'm saying A as if we're looking at the last example, we put 0 here into our stack as our starting vertex. Again, we could have started anywhere. I'm going to start at 0. So what is the process? It says pick a vertex from the stack. In this case, it's 0. We're peeking the top of the stack. Mark it as visited. So 0 is now visited. And then what do? After marking it as visited, it said find 0's first unvisited neighbor and push it into the stack. So let's just go in ascending order. What are the unvisited neighbors of 0? Well, 0 is connected, as we can see, to 1 and to 3. Neither of those are visited, so let's add 0's first unvisited neighbor in ascending order to the stack. We put a 1 in the stack. Done. Next iteration. What do? We're going to look at the top of the stack. We see a 1. We're going to mark it as visited. And we're going to find 1's first unvisited neighbor. Well, 1 is connected to 0, 3, 2, and 5. Again, I'm just looking across right here. 1 is connected to 0, 3, 2, and 5. 0 is already visited, but 2, 3, and 5 are unvisited. So what we're going to do is we're going to pick 2, the first one, and we're going to put it into the stack. Next iteration, look at the top of the stack. We're going to peek it. We see a 2. We mark 2 as visited, and we push into the stack 2's first unvisited neighbor. Well, 2 is connected to what? 2 is connected to 1, to 5, to 3, and to 4. Well, from those vertices, 1 is already visited, but 3, 4, and 5 are not visited. So we're going to push 3, the lowest one, into the stack. Continue, rinse and repeat. We're at 3. We're going to mark 3 as visited, and we're going to find 3's first unvisited neighbor. So what are the neighbors of 3? It's 0, 1, 2, and 4. From those, 0, 1, and 2 are already visited. 4 is the only one that is not visited, and so we're going to push 4 into the stack. And next iteration, we pull out 4, mark 4 as visited. And then when we mark 4 as visited, we need to push back into the stack all of 4's unvisited neighbors. 4 is connected to 3, to 2, and to 6. 3 and 2 are already visited. 6 is unvisited, so we push 6 into the stack. We pull out 6, or we access 6, we mark it as visited, and we ask, does 6 have any unvisited neighbors? Well, 6 is connected to 4, 6 is connected to 1, and that's it. And both of those are already visited. Well, because they're already visited, we don't have anything to push into the stack, and rather what we're going to do is actually remove 6 from the stack. Now we're back to the 4 at the next iteration. And we look at 4. We mark 4 as visited. And now we need to do what? We need to push into the stack any of 4's unvisited neighbors. Well, 4 is connected to 2, 3, and 6. All of them are already in the stack. We're going to pop out 4, therefore. Now we come to 3. 3 is the top of the stack. mark 3 as visited. It's already visited, no harm, no foul. We mark 3 as visited, and we need to push into the stack any of 3's unvisited neighbors. All of 3's neighbors, 0, 1, 2, and 4, are already visited, and so therefore 3 also gets popped out of the stack. We're now at the 2. We mark 2 as visited, no harm, no foul, it's already visited, no problem, we mark it again. And we need to do what? We need to find any of 2's unvisited neighbors, and we need to push them into the stack. Well, 2 has 4 neighbors, 3, 4, 1, and 5. 3, 1, and 4 are already visited, as we can see here, right? The 3, the 1, here's the 3, the 1, the 4, and the 5. Well, the 3, the 1, and the 4 are already visited. 3, 1, and 4 already visited, but the 5 is not. So we're going to do what? We're going to push the 5 into the stack. And so now at the next iteration, we will have finally visited every vertex, because we're going to, at the next iteration, peek the top of the stack, and we're going to see it's a 5. We're going to mark 5 as visited, and then we're going to do what? We're going to push into the stack any of 5's unvisited neighbors. Well, 5 is connected to 1 and 2. They're already both visited. Therefore, we're going to pop the stack. We come to the 2, mark it as visited. There are no remaining unvisited neighbors of 2. We pop the stack. Same thing for the 1. There are no remaining unvisited neighbors. And we're at the 0. There are no remaining unvisited neighbors. Not that bad, but it's super important to actually go through a full example and understand how that works with a DFS. And what we can do is do that exact same example now with doing a breadth first traversal. And I'm reminding both the listener, myself as well, that breadth first traversal, what are we going to do? This initial state, we're going to go ahead and put in that first vertex into the queue, and we're also going to mark it as visited. That's a difference. And what's going to happen at every single iteration? We're going to dequeue. We're not going to peek it. We're just going to dequeue. We're going to find all of its unvisited neighbors. We're going to mark them as visited, and we're going to enqueue them. And that is really the algorithm. So let's come over here to the tab. And through the magic of pause, we are able to start. So 0 is already in the queue, and 0 is already visited. What does the algorithm actually say we do? We need to dequeue. This is the first iteration. Dequeue that 0. What do we then do? Find all of 0's unvisited neighbors, mark them as visited, and then put them into the queue. So we're going to, I'm just going to scratch it. I'm just going to dequeue the 0, so I'm scratching it off. We're going to find all of 0's unvisited neighbors, which are just 1 and 3, mark them as visited, and also put them into the queue. That's it. Rinse and repeat. Come to the 1, dequeue it. This is the next iteration. Find all of 1's unvisited neighbors. Well, 1's unvisited neighbor, or 1's neighbors are 0, 3, 2, and 5. 0 and 3 are already visited. 2 and 5 are unvisited. So we put 2 and 5 as visited, and we also push or enqueue those values into the queue. Rinse and repeat. We're now at 3. Dequeue the 3. Find all of 3's unvisited neighbors. 3 is connected to 0, 1, 2, and 4. 0, 1, 2 are already visited. 4 is not. Mark 4 as visited, and enqueue 4. Continue. We're at the 2 at the next iteration. Dequeue the 2. Find all of 2's unvisited neighbors. 2 is connected to 3, 4, 1, and 5. 3, 4, 1, 5. They are all already inside the queue, and so there's nothing left to happen on the iteration. Next iteration, we come to the 2. We come to the 5. We're going to dequeue the 5, and we're going to enqueue, or we're going to look for all of 5's unvisited neighbors. Well, 5 is connected only to 1 and to the 2. They are both already visited, nothing else to happen at that iteration. And we're finally at the 4. What do we do here? We dequeue the 4, and we're going to find all of 4's unvisited neighbors. 4 is connected to 3, into 2, into 6. 3 and 2 are already visited. 6 is not. That was the last remaining vertex. We mark 6 as visited. We put 6 into the queue, and the next iteration, what do? Is we dequeue the 6. And we find all of 6 unvisited neighbors. 6 is connected only to 1 and 4. They are both visited, so there's nothing left to dequeue. The queue is also empty, and that is when the algorithm will end. And And that's it. That is your depth first traversal and your breadth first traversal of a graph. Here's the one we showed previously on the slides. Again, giving us a different ordering of that traversal of visiting those nodes. Was it captivating? I don't know. A despair.com demotivator. Destiny. Some are destined to soar in the wings of eagles. Ouch, while being torn apart by beaks and talons. Horrible. Despair.com, though, great website. As always, it's been fun. Have any questions, feel free to leave a comment. Take care, everyone.